Okay, let's finish up this first page of notes on the law of gravitation, and then we'll move on and do some more practice with it, just so you can get more familiar. All right, last time we calculated the force of gravity between the Earth and the Moon. 1.99 times 10 to the 20th newtons. That's a huge force. That is extremely big, okay? It makes sense because we have two very massive objects, the Moon and Earth. Earth, it doesn't look, I mean, if you look at the exponent numbers, you see that it's, the exponent is 2 bigger. That basically means it's 100 times more massive than the Moon. I think the actual number is about 81 times more massive. But we do have two truly massive objects, even though they're separated by millions of meters. The mass of the objects makes up for that, and so we have such a big force of gravity between them. How would the force of gravity change if the Moon were 3 times as massive and the Earth were twice as massive? Well, we're going to do this algebraically again. We're not going to plug in new numbers. I could just take the Earth, multiply this, the Earth's mass, multiply this by 2. I could take the Moon's mass, multiply this by 3, and then plug in the numbers all over again. But again, I don't want to do that. What if I plug something in wrong? What I'm going to do instead is the same thing I did up here. Okay, I don't have to call it FG1. Okay, I can call it whatever I want. I could call it FGA, FJB. I could even put like a little star next to it. The only reason I'm writing it like this, I'm going to write FGA, just so we know that we're talking about a different force from before. All I'm doing is I'm differentiating. I'm saying, hey, we're dealing with a different force of gravity, and any of the factors that change, I'm going to put that A next to them as well. G is a constant. That doesn't change. So now I'm going to have M1A, because we're changing the mass, M2A, and if you don't want to do this, fine, but you don't have to. But I'm trying to show you this is how I like to differentiate these things, okay? I'm not saying you have to do it the exact same way I do. The radius doesn't change, so we're just going to do regular old r squared. If the Moon is 3 times as massive, then that means that M1A is equal to 3 times the original M1. Earth is twice as massive. That tells us that M2A is equal to 2 M2. So I'm going to make those substitution changes in here. So I'm going to have G 3M1 times 2M2 over r squared. Now, one of the nice things about multiplication is the order doesn't matter. This says right now to do G times 3 times M1 times 2 times M2. Oftentimes what I'm going to want to do is I want to put all of the letters together and all the numbers together. I'm going to pull these numbers out to the front. So I'm going to have 3 times 2 times G times M1 times M2. And actually, we all know that 3 times 2 is 6. So I'm going to multiply the 3 and the 2 together. I get 6. I'm going to bring that out to the front and have 6G M1 M2 over r squared. And again, look what I have here. G M1 M2 over r squared is simply the force of gravity from the initial problem. So I see I have an extra factor of 6. The new force of gravity is 6 times the original force of gravity. Makes sense. We tripled the Moon's mass. We doubled the Earth's mass. Tripling means multiplying by a factor of 3. Doubling means multiply by a factor of 2. I take the 3 and the 2. I multiply them together. I get 6. All this is a way to show that kind of factor thinking, how the factors in this equation have changed. So 6 times 1.99 times 10 to the 20th newtons means that the new force of gravity is approximately, lost my reference here, 1.193 times 10 to the 21st newtons, 6 times the original. Before we get into some more examples, I do just want to make a quick note about one thing. I see it come up every once in a while. It might seem kind of weird to you how gravity works. Every other force that we've talked about so far, the objects that are exerting forces between each other are directly touching. Gravity is the only one where you don't need objects that are directly touching. I mean, the Earth and the Moon are millions of meters apart. They're not directly touching each other. Why are they exerting an influence on each other? And it turns out that what happens is that every mass, any object that has mass, creates what is known as a gravitational field around it. These masses actually alter the space around them and allow for forces between objects that are not touching because they're altering the space around them. You don't have to know that much about gravitational fields for this class, but you do need to know what the pictures generally look like. Pictures of these fields show the direction of the force of gravity at different points near an object by using vectors. So we're going to draw two very basic gravitational fields. Let's say that you're looking at the Earth from kind of up close. Okay, so you've got like an up close view, and by up close I mean like we're pretty zoomed in on the Earth. This is the curve of the Earth's surface. If we were drawing the gravitational field, we would have something like this. We would have some vectors pointing down to show the direction of the force of gravity at these different points on Earth's surface. Notice that the vectors don't all point exactly down in terms of my paper, but they all do point towards the center of the Earth. And actually, I'm going to add in some little smaller vectors up here to show that the gravitational field is weaker the farther away you get from Earth. But they're still perfectly lined up. So the size of these vectors shows that the Earth's gravitational field is stronger when we're closer to the Earth. Now let's take a look at Earth from far away. Where we can see the whole Earth. Well, zooming out, I mean, it's pretty much the same picture. The gravitational field would just look like this. The vectors represent the direction of the gravitational force at different points, and since gravity is attractive, they're all pointing towards the center of the Earth. We're going to move on now. We're going to do practice with Newton's law of gravitation. Here we go. All right, easy example to start off. A bowler trying to knock down a 2.5 kilogram bowling pin releases his 5 kilogram bowling ball at the end of the lane 20 meters away. As he releases the ball, what is the magnitude of the force of gravity between the ball and the pin? Well, we can't use Fg equals mg here because we're not dealing with the force of gravity between the ball and the Earth or the pin and the Earth. We want the ball and the pin. So we have to use the universal law of gravitation. G m1 m2 over r squared. I have numbers for m1, m2, and r, and I know g is a constant, so I can just plug in. G is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. M1, let's make M1 the mass of the bowling pin, 2.5 kilograms. M2 would therefore be the mass of the bowling ball, that's 5 kilograms. And the distance between the bowling ball and the pin and the ball is 20 meters. Again, do not forget that that's 20 meters squared. 6.67 EE negative 11 times 2.5 times 5 divided by 20 and divided by 20 again because it's squared, and I end up with a force of gravity between the pin and the ball of 2.08 times 10 to the negative 12 newtons. Very small, and that makes sense because we're dealing with normal size objects, okay? That's extremely small. That's basically not noticeable, but it is there. The force of gravity works between all objects. If the bowler had used a 2.5 kilogram bowling ball instead, how would the force of gravity be different? So because this is problem B, I'm going to do FGB. Again, that last subscript doesn't matter. That's just me showing you that this is different from before. Okay, what's different? It's the mass of the bowling ball. You could probably almost do this in your head, but this is good if you want to be able to show the work. G stays the same, M1, which is the pin, stays the same, but M2, let's see, 2.5 compared to 5, M2B is 1/2 of the original M2. I guess I don't really need parentheses for that. I don't know why I put those in. Equals r squared. So this is going to change because it's now G M1 1/2 M2 over r squared. I'm going to move that 1/2 all the way out in front. So this is going to be 1/2 times G M1 M2 over r squared. And I can bring it all the way off of the fraction if I want to, or I could keep it on top of the fraction because it's in the numerator. G M1 M2 over r squared is right here. That is equal to the original force So I know that the new force is half of the original. That makes sense. We decrease the mass by a factor, or we cut the mass in half. We should be cutting the force in half as well. That makes sense. So we have 1/2. Let's see, the original force of gravity was 2.08 times 10 to the negative 12 newtons. The new force, if I multiply this by 1/2, is 1.04 times 10 to the negative 12 newtons, half of the original. When the 5 kilogram ball was 3/4 of the way to the pin, how has the force of gravity changed? So let's say that the original ball, the 5 kilogram ball, it's 3/4 of the way to the pin. What's changed here? Well, if I want to think about what's changed, the masses are the same as before, it's just now much closer. If it's 3/4 of the way to the pin and the distance between them was 20 meters, that means it's only 5 meters from it. Okay, it's 3/4 of the way there. It means it's past halfway. It's less than 10 meters away. It's only 5 meters away now. So I could, again, plug that number in here and do the calculation all over again. Or I can realize that 5 meters is the same as saying that R, and I'm going to call it RC, is 1/4 of the original R, 1/4. So if I want to write this algebraically, I say FG in problem C is G M1 M2 over RC squared. G M1 M2 don't change. However, RC is equal to 1/4 R, and that whole thing has to get squared. Which means when I square this, I am squaring not only the R, but also the 1/4. And if I take 1/4 and I square it, and of course, I forget how to make this into a fraction on here, but if I square 1/4, that means I'm squaring the 1 and I'm squaring the 4. 1 squared is 1, 4 squared is 16. What I end up with in the denominator here is 1/16 R squared. Now, I have a fraction in the denominator of a fraction. That's annoying. It looks weird. Dividing by 1/16 is not the same as dividing by 16. It's the inverse of that. Dividing something by 1/16 is actually the same as multiplying by 16. So if you're ever stuck with a fraction in the denominator of a bigger fraction, here's a little trick you can do. If it's 1/16 on the denominator of a fraction, and so if you're dividing by 1/16, that's the same as multiplying by 16. Okay, if you don't believe me, try it out. So if I take 16 and I divide by 1/16, I get 256. 16 times 16 is 256. That means that the new force of gravity between these two is 16 times the original force of gravity. The original force of gravity was 2.08 times 10 to the negative 12th. So this is 16 times 2.08 times 10 to the negative 12th. And we get FGC equals 16 times 2.08, 12, 3.33 times 10 to the negative 11th. Okay? The fact that that exponent went up means that we really did increase the force of gravity by a substantial amount. All right. Let's see here. We've got a time for, let's see, I think we'll do 2 more sets, so some of these questions are related. Number 2, what is the force of gravity between a 60 kilogram person and the Earth? Okay, pretty straightforward. Fg equals G M1 M2 over R squared. I know that big G is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. 60 kilogram person is a mass of, well, 60 kilograms. The Earth's mass, from our reference tables, mass of the Earth, 5.98 times 10 to the 24th kilograms. Now you might be asking yourself, well, how far apart are they? Okay, let's assume that the person's on Earth. You might be tempted to say they're 0 meters apart since they're touching. Remember that R is the distance between the centers of those objects. So if you have a person standing on Earth, how far apart is the person's center from the Earth's center? Okay? Let's assume, okay, so obviously this is in the scale. The person's center is approximately 1 Earth radius away from the Earth's center. Wouldn't you know it, we have a mean radius of Earth, 6.37 times 10 to the 6th meters. And we need to square that. 6.37 times 10 to the 6th meters. So we end up with, let's see, okay, we're going to multiply everything. We're going to divide by 6.37, E6, square it, and the parentheses. Okay. We end up with a force of gravity of 589.8 newtons. Now, the especially thoughtful watchers of this video might be saying, wait a second, we already know how to find the force of gravity between the person and the Earth using a much simpler method. If we're finding the force of gravity between something and Earth, we just use Fg equals mg. Let's see if we get the same thing. 60 kilogram person times 9.81 meters per second squared. We don't get exactly the same thing, but we get pretty much the same thing. The reason we don't get exactly the same thing is because, obviously, 9.81 meters per second squared is rounded itself, and also this total has been rounded a little bit. Okay? So like things like the Earth's mass and the Earth's radius have been rounded, and even this constant has been rounded a little bit. But the fact that we get basically the same thing, that should make sense. We're calculating the same value using 2 different ways. It makes perfect sense that we should get the exact same thing. Okay? So we get the exact same value. So if you're dealing with the force of gravity between the Earth and a person, take the easy way out. Fg equals mg. If you're dealing with the force of gravity between any two objects and one of them isn't the Earth, and the other object isn't on Earth, then you've got to use this. If the gravitational force is the only force acting on that person, determine the gravitational field strength of the Earth at that point. In other words, figure out the acceleration due to gravity. One thing that I would like everyone to note, on our reference tables, on the back mechanics section, oh, by the way, Fg, I don't even think I showed you this yet, Fg equals g m1 m2 over r squared. M is mass, r is, not in this case, not radius, but distance between centers. When we look at little g, that's acceleration due to gravity or gravitational field strength. It means the same thing. So, if we're looking for the gravitational field strength of the Earth, that basically means solve for little g. Well, wait a sec. This is kind of obvious. If that's the only force, then that must be equal to ma. If the force is, let's use this one since that's what we derived using the force of gravity equation, 589.8 newtons equals 60 kilograms times A. We see that A is 8 divided by 60. We actually get 9.83 meters per second squared. So, and actually the unit, so if you want to go by this, the units are newtons per kilogram, which is the same as meters per second squared. Due to some rounding errors, and actually a few other smaller factors that we will not get into this year, this is basically the same as our very familiar 9.81 meters per second squared. Now here's an interesting question. What would Earth's acceleration be? You might be like, what? What do you mean? Earth doesn't accelerate towards us. Well, yes, it does. Because the Earth and us are interacting via the force of gravity, the force that the Earth puts on us is the same as the force that we put on the Earth. Let's assume, even though it's not true, that our force on the Earth is the only force that the Earth experiences. We can figure out the Earth's acceleration. We put a force of gravity on the Earth of 589.8 newtons, and in order to find the Earth's acceleration, we divide by the Earth's mass. Earth's mass is 5.98 times 10 to the 24 24th kilograms. We solve for A, 589.8 divided by 5.98 E24. We get 9.86 times 10 to the negative 23rd meters per second squared. Negative 23rd is imperceptible, too tiny to ever notice, okay? Way too tiny to ever notice. We'll do 5, 6, and let's see here. We can probably get up to, we might not make it quite. Yeah, we could probably try and get up to 8 though. Find the magnitude of the force of gravity between the sun and the earth, with the mass of the sun being 1.99 times 10 to the 30th kilograms. If you get these types of questions, as long as you know how to use a calculator and understand this equation, these are gimmies, okay? All it's asking you to do is plug some numbers into a calculator. Very straightforward. There's G, mass of the earth, again, 5.98 times 10 to the 24th kilograms. Mass of the sun, 1.99 times 10 to the 30th kilograms. And we do need the distance between the sun and the earth. It's good to familiarize yourself with about, let's see, 1, 2, 3, 4, 5, 6. These 6 numbers in the table right here. Know what you're given, know what you're not given. Mean distance from the earth to the sun, 1.5 times 10 to the 11th meters. Squared. So the force of gravity between the earth and the sun, oh, let me move this up for you a little bit. Is approximately 3.53 times 10 to the 22nd newtons. You'll notice it's a little bit bigger of a force than between the Earth and the Moon. The Sun is much, even though the Sun's farther away, it's much, much, much more massive. How would the force change if the Sun was 3 times as far away? Okay. Fg1 equals G m1 m2 over r1 squared. If the sun is 3 times as far away, that means r1 equals 3r. So we do 3r squared. Notice the squared is outside the parentheses. It's 3r, all of that is getting squared. Let's see, if we square 3r, we should get 9r squared. And so we end up with an extra factor of 1/9 times the original force, which means we take 1/9 times 3.53 times 10 to the 22nd newtons. The new force, oh, nope, that's not what I want to do, divided by 9, 3.92 times 10 to 21st newtons. I think you can see that. Yep, there you go. All right. A couple more examples, then we'll call it for this video and move on to the next. How would the force change if the separation between the Earth and the Sun were normal, but the Earth was 5 times more massive? Fg2 equals G. Let's see, Earth was, so let's see, this is going to be M2 equals 5 of the original M2. Oh, M1, my bad. And I know it can get confusing with all the 1s and 2s, but again, that's just my system for doing it. You can adopt your own system. Double check something. Okay, yep, we're good. Okay. We're going to bring the 5 out front. 5g m1 m2 over r squared. 5 times the original, which is 5 times, what was it, 3.53 times 10 to the 22nd. Newtons. So the force of gravity is equal to 1.76, not actually 5, there's some rounding, times 10 to the 23rd newtons. We're going to call it there. We'll pick up with 8, 9, 10, 11, 12 in the next video. 8 is actually part of this example, but we'll cut it off there and we'll do it in the next video. Okay?